Okay, so we're going to take a look at another shear moment diagram, and this one's a little bit different. If you're looking for reactions, I'll post a link to the video on how to do reactions below. But what we're going to do here is we're going to start with, basically we're going to jump right in. So basically we've said we've already solved for reactions, but we've got a beam and it has two, point loads here, and what we want to do is we want to find the place where there's the maximum shear and the maximum moment. So to do that, we're going to draw the shear and moment diagrams, right? So to start, right, what we're going to do is we're just going to jump in with a shear diagram. So here's our shear diagram, here's our baseline. This is like our zero shear, no shear. And when we start on a beam, we're going to start at zero shear. So when we start at the end of a beam, there's really no force, but as soon as we hit this 4 kips, we're going to pick up 4 kips worth of shear. That's going to push us down on our shear diagram. So we'll draw that in, and there's our 4 kips. We'll label this as -4 because we went down. Okay, in between the -4 kips and the 7 kips, there's no change in shear. So all the way, from this point left on the beam all the way to the first support, until we hit the first support, we're going to have 4 kips. So let's draw that. All right, so there's our -4 all the way to the support. And then when we hit the support, right, we're going to have 7 kips. And this 7 kips is going to push the shear diagram up 7 kips. So what this is going to look like is we're going to have a line that goes up 7 kips. Right, so the height here is going to be 3 kips, and what that means, right, is this distance, right, is 7 kips. That is equal to, our AY, our reaction at AY. Okay, so that whole distance here is 7 kips. It goes from -4 plus 7 gets us to 3. And then you'll notice the shear doesn't change at all until we hit the 6 kips. So what that means is we're going to come straight across until we hit the 6 kips here, and then when we hit the 6 kips, it's going to push us down 6 kips. So it's going to push the shear down 6. Okay, so let's look at that. Okay, so 3 kips, minus 6 kips. So if I draw that in here, right, this is going to be, -6 kips, and that's like BY. So when we come down -6, we're going to get to a point over here that's -3 kips. And this is kind of cool because when we continue our shear diagram from this 6 kips over to the 3 kips, let's look what happens. So we bring it over, and you'll notice now we have a 3 kip force that's pushing us back up to 0. So we'll come right back up to 0. And when we do that, our shear diagram also closes. So what I like to do is I like to go ahead and highlight this to show where the areas are, just so we don't get confused. So we'll do that quick. We have area 1, area 2, and area 3. Right, so these are the different areas of the shear diagram, right? We have a positive area in the middle here and 2 negative areas. And those positives and negatives, they're going to be important because when, we go ahead now to this next step, well, we just drew the shear diagram. What we want to do next is we want to go ahead and draw the moment diagram. So to do that, what we want to do is we want to go from kind of left to right and add up areas. So, if this is point 0, we'll call this point 1, call this point 2, and call this point 3. And what we want to do is we want to find the moment at each of those points. But to do that, what we're going to do is we're going to find each of these areas. So I'm just going to call this A1, this A2, and this A3, right? So what we need to do is we just need to find areas, right? So when we're integrating this area, what we're doing is we're just solving for an area. So to do that, what we're going to get is we have A1 equals, we have -4 kips, right? That's the height of this rectangle, times the distance of, well, we have 3 feet. So -4 kips times 3 feet. What's that? Well, it's -12 kip feet, right? And you'll notice units here. Units are in moment. So when we draw our first, moment line here, we're going to come down to our moment diagram. We know we're going to come down to -12 kip feet. Before we do that, let's just finish here. We'll go through, we'll find all our areas, then we'll find the moment. So area 2, what do we have? Well, we come up to a height of 3 kips. So that's going to be 3 kips times a distance here of 5 feet. So we get 15 kip feet, right? And then our last area here, area 3, what do we have? Well, we have, -3 kips times 1 foot is going to be -3 kip feet. Okay, so as we go across here, I'm just going to scroll this up a little bit. And as we go across, what we want to do is we want to plot our points. So the moment at 0, right, the moment at 0 is just going to equal 0 kip feet, right? We're at the end of a cantilever here, and at the end of the cantilever, there's no applied moment, so there's really no rotation here going on. It's just a force pushing down, but there's really no internal moment at this point. Okay, what that moment is going to be is that we're going to start at 0. There's also no area to the left of this, no applied moment, no area to the left of it. The moment's going to be 0. Okay, when we go to moment at 1, well, what are we going to do next? What we're going to see here is the moment at 1 is just going to equal the area from 0 to 1. So what is that? Well, it's A1. So the moment at 1 is going to equal A1, which equals, minus 12 kip feet. Okay, so we can come down, we can plot that. So what are we going to do? I'll plot it so that every block here is 3 kip feet. So if I come down here, I'm at minus 12, and I already have my units over here, so I don't need to write the units again. Okay, and then what we're going to do is let's look at the moment at point 2. Well, again, what we're doing is we're adding up all the area from left to right, so from 0 all the way up to 2. So what's this going to equal? Well, it's really just going to equal A1, plus A2. We could also say this equals, M1 plus A2, right? It's the same idea. What we're going to get here is we're going to get, minus 12 kip feet plus 15 kip feet, and that's going to equal 3 kip feet. Okay, so when we add up the areas from left to right, that's where we end up. So we're going to come up and we're going to end up right at 3 kip feet. So I can label this as well, either on the right hand side or the left hand side. But then we'll come here and we'll say the moment at 3, this is going to equal A1 plus A2 plus A3, so hopefully you're getting the hang of this. We could also say it's just M2 plus A3, and when we do that, I'm just going to use M2 here, but what we get is 3 kip feet minus 3 kip feet, and that equals 0, which is good because what we would expect is at the end of a simply supported beam here with a roller where there's no applied moment, we're going to go back to 0, right? So there are points, right, but now we need to connect them. And the cool thing about this is the height of the shear diagram is equal to the slope of the moment diagram. So what that means is if we have a height of minus 4, we have a slope of minus 4 kips per foot. So in other words, when we connect the dots here, this is going to end up being a straight line. So that line looks, something like this, where we go, down. The slope here, right? The slope here is going to be for every foot we go over, we go down 4 kips, right? That's equal to this height of the shear diagram. That just helps us to understand where this comes from, right? And then when we go here, what we're going to do is we're going to go up at 3 kips per foot until we hit 3, right? We're going to go up this area, this 15 kip feet, right? Between minus 12 and 3, we're going to go up 15 all the way to this point. And to connect that, since we have a constant, slope horizontal line, a horizontal line shear here, we're going to have a linearly sloping moment diagram. So that moment diagram is going to come up and just, end like that. Okay. And then to get back to 0, again, we have a constant slope here, so hopefully you can see this, minus 3 kips per foot over 1 foot distance. We're going to go down at that slope. And our moment diagram closes back to 0. So there's our moment diagram, right? So I can shade this in. And once I shade it in, I can also say here, well, now that I know, now I have my shear and moment diagram, I can identify the point of maximum moment, right? So we have 2 things going on here. In this problem, it's a little bit different than the last version of this video where we just had a 1-point load. So in this problem, with the 2-point loads and the cantilever, what we notice is at this point we have a negative moment. And what a negative moment is really, this is just, this deals with sign convention. We'll talk about that in a minute. But basically our max, M-max, and I'll just label this, negative, is going to be, minus 12 kip feet. And our M-max positive moment is going to be, plus 3 kip feet. So this takes, the maximum moment here, the maximum moment here, and it kind of highlights which each of them are. So whenever we have a negative or positive moment, what I like to do is I like to draw my little force element here somewhere in the beam. And what we say is a positive moment is the sign convention we're going to use, causes tension on the bottom and compression on the top. Right? So what does that mean? Well, it also means if we have a negative moment, right, it's going to be the opposite, right? So the negative moment is going to cause tension on the top and compression on the bottom. Okay, so if we think about this, it doesn't make a huge difference if we have a beam that's symmetric about its x-axis, but if we have a beam that's non-symmetric, like let's say a composite beam or something along those lines, where the negative versus positive moment is going to make a difference. Okay, but for generally what we're going to be doing as we get started here with symmetric shapes is we're just going to be looking at the biggest magnitude. So in this case, we're looking at the minus 12 kip feet. And that's really a decent answer. And if you're looking at it, I would list both of them if you weren't sure. But in general, right, we're looking for the biggest moment magnitude, right? If you're not told that it's an unsymmetric section or something along those lines, you could ask. But at least this gives you sort of a framework. And again, we could look at the shear max. And shear, again, we're not as concerned. Again, it depends on the section, but in this case, the maximum magnitude of that shear is going to be minus 4 kips. So at the end of it, what do we have? We figured out our maximum moment, our maximum shear, all by drawing a shear and moment diagram. So there we did it. We solved for the reactions, we drew our shear and moment diagram, and we're good. So if you have questions, feel free to drop a comment. Otherwise, keep working hard and keep moving onward and upward.